start recording, share. Why is that happening? Okay. Okay. Okay, I got too many screens here. All right, let's do okay. So where we left off in your notes was some stuff on convergence. And today, what I want to do is talk about functions. And where we're headed to is power series. But before we do that, I realized there's a part in the class that I kind of took out for time and I want to put back in. I don't have anything that's assigned in the homework right now, but we'll need to use it later, and that's the algebra of series. Namely, what we're looking at is the addition, subtraction, and particularly the multiplication of series in order to get better convergence. In other words, we're going to try and make a series converge faster. So if we look at the rate, we can change this, or we can adjust it by multiplying another series or a polynomial and then adjusting the constants of the polynomial. So for example, and this is kind of a long example, but it's worth doing. We look at the function a natural log of 1 plus x. You may be aware, I'm sorry, I've got things on different screens. I need to be able to look at you. All right. You may be aware that you can represent this as a series, namely the sum from n equals 1 to infinity of minus 1 to the n minus 1 x to the n over n. And this converges pretty slowly on the interval minus 1 x 1. Let's do 1. So this is slow, by which we mean it converges as 1 over n. So what can we do? One thing we can do is, and this is the kind of trick that comes with practice, that you just get used to knowing how many terms you need. Multiply both sides by 1 plus a1x, where a1 is a constant. And then we can see what that does. So we have 1 plus a1x times ln of 1 plus x. That equals the sum from n equals 1 to infinity of minus 1 to the n minus 1, x to the n over n. That's just the 1, plus a1, that adjustable constant, times n, a sum from n equals 1 to infinity of minus 1 to the n minus 1, x now to the n plus 1 over n. Just multiplied both those terms through. And what we're going to do is take all of this and realize we can separate out an x term. And now we have a sum from n equals 2 to infinity. We're just taking the first term of that first series of minus 1 to the n minus 1 x to the n over n, plus that constant a1 times that sum again. So this is the same sum. Oops. N equals 1 to infinity of that same sum. And now we'll just take this and rewrite this so that this is all under one summation. This is x plus the sum from n equals 2 to infinity of minus 1 to the n minus 1, x to the n over n plus a1, and then we just rewrite the subscripts or the superscripts, so a minus 1 to the n minus 2, x to the n over now n minus 1, right? Just because we've just changed the indices. Everybody with me? Just a bunch of algebra, but it does pay off. All right, so if we continue this, this is equal to x plus the sum from n equals 2 to infinity of minus 1. Now we're just collecting terms, n minus 1 times 1 over n plus minus 1 to the minus 1, a1 over n minus 1, now all times x, x to the n. So then that's equal to, I did this right, x plus the sum over n equals 2 to infinity of minus 1 to the n minus 1 times 1 over n minus a1 over n minus 1. Okay. And now this is as far as we go unless we do something with a sub 1. So if we let a sub 1 be equal to 1, then this series becomes x plus the sum from n equals 2 to infinity of minus 1 to the n minus 1 times n times 1 minus a1 minus 1 over n times n minus 1 to the x to the n. We're just combining those two fractions. And so what that means is we have 1 plus x times ln of 1 plus x, which is the function that we started with, is equal to x plus this sum, n equals 2 to infinity of all of this minus 1 to the n minus 1. Whoa. Rearrange things a little bit. Minus 1 over n to the n minus 1 times x to the n. And so finally, we have that we can represent this series instead of a series that converges to n to the minus 1 as all of this x plus this sum n equals 2 infinity. I'll just put all of this in brackets, divided by 1 plus x. But because now we've got this term, this series, this new series, we'll call D2, converges as n to the minus 2. So the point here, apart from all of this algebra, is that we can, by multiplying both sides of this expression for a function, we can create a different series that converges faster. That is, we need to use fewer terms. Okay? And as an example of this, we can ask, let's let x be equal to 0.9. Ln of 1 plus x in that case is 0.641854, and so on. If we take a look at our infinite series and just look at the partial sums for the original series, we get S1 is equal to 0.9, obviously. S2 is equal to 0.9 minus 0.9 squared over 2, if you look at what the original setup was. And that's equal to 0.495. S3 is equal to 0.738. And basically, by the time you get to S10, you've got 0.625. This is with the original series. With the new series, by the time you get to the partial sum of 2, or S2, you get 0.687, 0. So in other words, if you can manipulate the series with the polynomial and change the constant, you can make something converge faster. And that's important if you're trying to estimate something based on a series, which we do all the time in physics. All right. Why don't you give me a thumbs up when you're done writing, and if you have any questions, you can go ahead. You can do the either, there you go. Should have some background music on.
Jeopardy music when we're all writing.
Yeah. I've already had a faculty meeting with Jeopardy music, so maybe some Tiger King songs. Oh, Lord. That came along just at the right moment. Everybody ready? All right. All right, so the next section is actually, so we've laid down all the groundwork, and the next section is the one that I think in some ways is most important, because you've used this without some of the mathematical underpinning, but in terms of the binomial and Taylor expansion, we're going to go into this a little bit more deeply, and there's some stuff in the homework as well. Make sure that you look at the homework. I have office hours today and tomorrow, and I'm going to send out an email to the department having basically open hours so that people can stop by. But basically, by the time we get through this, we'll have covered most of the stuff on the first homework. So anyway, a series of functions. What are we doing here? Well, let's start with the definition. What the fuck? Excuse me. There we go. All right. So we're going to consider a function, a series, as a collection of functions of x. What's important here is that we are going to, at some point, have coefficients that's basically a sequence of numbers, as well as a function, right? So at some point, we'll have something that looks like that. We're right now focusing on a series of functions and what we can say about how they converge. We already have used this in a number of cases. We can, if we're defining this series, we can define sums. So we have the partial sums in the usual way. Again, this is a function of x, so 2 of x to u sub n of x. And we can have the series, the functional sum. And I'll get to what that means in just a second, but that is the limit, just as in the last case, as n goes to infinity, of these partial sums, right, where this is equal to the sum over all these terms. And what we mean by that is that we're not summing necessarily to a particular number, right? We're summing to a particular function. So if you think about, for example, Fourier series, that's essentially what we're talking about. And in order to make this useful, we need to understand when these series converge. And there's a particular, I didn't turn Siri off on my phone. Shit. Sorry. God damn it. Look, it's all a grand experiment. Okay. What we're trying to do is look at when this collection of series converges to a particular function. In other words, when can we approximate a function by something that's much more simple? And ultimately, especially when we're talking about uniform convergence, into a sort of a piecewise integrable form. So what we're going to, let's start with a definition. We'll use the Arfken definition, essentially. We're going to consider a small region, any small number epsilon, that's greater than 0, I guess if, but all right, there exists a number n independent of x in the interval a, b, such that the absolute value of the sum of x, that is what we expect this series actually to represent when it finally converges, when you use all of those terms, minus one of the partial sum up to some value of x is less than this epsilon for all n, greater than n, capital N. Then this u sub n of x is uniformly convergent on that interval, or in that interval. All right. So what does that mean? It's a bit of a word salad, but if you consider basically your function s of x, so this is what your series of functions are summing to. What this is saying is that consider a distance that is s of x plus epsilon, and a series that's s of x minus epsilon. And your partial sum for any given term might look something like that. That's your s sub n of x. And this is uniformly convergent on, say, x, on the interval x equals a to x equals b, if you can find a partial sum that is in this arbitrarily small region, right? In other words, can you take enough terms to approximate this function to whatever tolerance value you set? Right? So that's what all of this means. I know that, I mean, for my reading, every time I've taught this class, I get kind of turned around with uniform convergence, but all it means is how good is your approximation, how many terms. Think of it again with the Legendre polynomials or the Fourier series, how many terms you need to adequately represent a function. Okay, are there any questions on that? Just the basic definition? Okay. So there are a couple of tests for that you can use to determine whether a series is uniformly convergent. I'll focus on one of them. And then we'll come back to the other later on. So this is the Weierstrass. Did I get that right? Nope. Weierstrass M test for uniform convergence. Okay. And the idea here is pretty similar to the things that we've seen before, especially when we look at something like the Cauchy test. So we're basically going to compare the function to a sequence that we know converges. So for example, if we take a sequence from I equals 1 to infinity called m sub I, such that m sub I is greater than or equal to all of the u sub I of x. For all x in our interval of interest, and this m sub I is convergent, then U sub I will be uniformly convergent on A, B. Okay, so it's a pretty straightforward test. Let me give you an example. So let's take a function g of x is equal to the sum n equals 1 to infinity of 1 over 3 to the n times cosine of x over 2n. And we're looking at this on all reals. All right. What could we use for m in this case?
You could just use 1 over 3n.
Yes. So if we consider that the absolute value of 1 over 3 to the n times cosine of x over 2 to the n is always less than or equal to 1 over 3 to the n, that suggests that we can use m sub n as 1 over 3 to the n. Okay? So if that's the case, what is that equal to? So I think we have a suspicion probably that this is convergent, but it's an important series, so what is it convergent to? What kind of series is this? Should I give you a hint? Starts with a G and rhymes with geometric series, right? So what's the sum for a geometric series? So if we had 1 over r to the n,
1 minus r to the n over 1 minus r.
right, and if we let n go to infinity, this becomes 1 over r, right? So this converges to a half, right? Because 3 is our r, and you find that convergence. The reason why I'm kind of hammering on this is that the geometric series, and especially its sum, is something we're going to see a lot of. In fact, in the homework, if you haven't looked at it already, there's a problem on Olbers' paradox, which is why is the night sky dark? That depends on using a fraction of the sky that is covered by intervening stars in shells, and that is a good example of a geometric series, right? Where you just have to figure out what is that r in order to show that all of the stars map out the total solid angle, which is 4 pi steradians. All right. Okay, so since this is equal to a half, that means that the series is uniformly convergent on all reals. Okay, so all you have to do is figure out a sequence that will converge, and generally speaking, that's going to be one of the geometric series. Okay. The other test I'm just going to mention is Abel's test. We'll look at that later. But here, this is when we use u sub n of x is equal to a sub n of times f of x, and we can use this if the sum of those terms come to a constant value. then basically if the function f of x is monotonic, then you can show that the u sub n of x is uniformly convergent. Okay. All right. The last thing that I want to say about this before we move on, and then I'll take any questions you have, is the reason why we care about this, and that is the properties of uniformly convergent series. Okay. So there are basically a couple of things here. One is that if these functions u of n of x are continuous, then f of x is equal to sum of n1 to infinity of u n of x, is also continuous. That's important, but not necessarily as important as the fact that we can write the integral from a to b of f of x dx as the sum from n equals 1 to infinity from a to b of these functions. And of course, how many of these terms that you keep depends on how quickly this converges. And then you can also do the same with the derivative. That is, it's equal to the sum, the infinite sum of the derivative of these functions. Right. And some of these things we've already seen and we will make use of right now. But we'll take a minute to have some coffee and rest your hands. And if you have questions, ask. The main idea here is that we can, as you already know, in some sense, use functional series to approximate more complicated functions. Okay. All right. Is this a good enough speed, by the way? My dog is barking. Okay. That means the mail's here. Okay. All right. So let's look at Taylor expansions. This is obviously, especially if you just took comp mech, something that we covered, you've seen this before, but it's worth reminding you where this comes from and the limits of its use. The first thing we'll start with is a derivation. And it's basically, what we're trying to do is to make successive approximations of a function by looking at how it's changing in different orders, right? We usually stop after one or two terms. But if we take a bit more of a rigorous approach, we'll integrate n times a function f of x that has a continuous nth derivative, so that we actually can have an answer. That is, we take a function and we're integrating from a to x, f to the n here of x1 dx1. That is, those are our dummy variables in the integration. We can represent this as fn minus 1, x1 evaluated from x to a. And that's equal to that, obviously. But if we keep doing this, right, we can develop essentially a series of embedded intervals. That's what that horizontal ellipses refers to different dummy variables all the way down to dx2, where we have dx1 f of n. This is the order of the derivative of x1. All of that is going to be equal to f of x, which is what we're after, minus f of a minus x minus a times f prime evaluated at a minus x minus a squared over 2 factorial a minus dot minus, let's see, x minus a to the n minus 1 over n minus 1 factorial f minus 1 evaluated at a. Okay, so all we're doing is taking something that we know has a bunch of derivatives and breaking out that integration, paring it down, right? So the definition of the Taylor series then is to approximate a function by successively high order approximations to the slope at a point of interest, right? In this case, a. So the definition of our Taylor expansion is then f of x is equal to f at a. That is, we're expanding around a point a, right? Oops. So this is f. So if we turn all of this around, we're just solving for f of x. So this is x minus a times that first derivative evaluated at a plus x minus a squared over 2. Just see if you're awake there. 2 factorial. We even get double factorials in this class. Have you guys ever used double factorials? I don't even know how to say that. 2! And half factorials and negative factorials. I love this class. We'll do that in a minute. All right, I've lost track. Second derivative evaluated at a plus these intermediate terms, n minus 1 over n minus 1 factorial, the n minus 1th derivative, plus a remainder, if we want to be completist about it. Okay. Where r sub n is just the remaining set of derivatives. If we stop that after the n minus 1th derivative. Okay, and I think, I mean, we've all seen this. When f of x is constructed such that the limit as n goes to infinity, that this remainder function is equal to 0, then we have our usual definition f of x is equal to f of a plus x minus a, f prime of a plus x minus a squared over 2 factorial plus a plus higher order terms that we're going to ignore. Or if we want to write this going back to what we've been doing the last couple of days as a series, we have f of x is equal to the infinite sum from n equals 0 to infinity. If we look at, this is the 0th derivative, first derivative, second derivative term. So this is x to the minus, or x minus a to the n over n factorial times the nth derivative evaluated at A. So that's f.4. Right, so this is our Taylor expansion about x equals A, right? And typically we don't let, or we don't use many terms. Hold on. Pretty straightforward. Hope so. You've seen it before. There are some other ways of writing this. And then we'll get into some examples. If we let x be equal to x plus h, and so h is a small number, then f of x plus h is equal to the sum from n equals 0 to infinity of h to the n over n prime, f, the nth derivative of f, evaluated at x. Now we're expanding it basically around a small value of this small h. You can also use the differential operator d. And you see this sometimes in fluid dynamics, where f of x plus h can be written as the sum of n from 0 to infinity of h to the n d to the n over n factorial f of x, which actually can be written as e to the h d f of x. So we can use that exponential function as an operator in this case. So those are maybe some ways of seeing it that you haven't seen before. The other thing that I'll say before I get into some examples is the special case of the Maclaurin series. Right? So the Maclaurin series is when a is equal to 0, that is, we're expanding about x equals 0. So f of x is equal to f of 0 plus x f prime of 0, and so on, and that equals the sum from n equals 0 to infinity of x to the n over n factorial of x evaluated at 0. And this is just another way of writing expressions for small values of x, right? Whenever we talk about what is the small angle formula and things like that, that comes from our Maclaurin expansion. Okay. How are we doing? Okay. Okay. So some examples, let's see. I won't do too many of these because you've seen a lot of these already, but if we let f of x be equal to sine of x, then we know that the Maclaurin expansion would include f of 0 is equal to 0, f prime evaluated at 0, right? And that's the key thing to remember, is that you're evaluating after you do the derivative. That's equal to plus 1. F double prime evaluated at 0 is equal to 0. F triple prime evaluated at 0 is equal to minus 1, and so on. So f of x is equal to 0 plus 0 minus x cubed over 3 factorial, or x minus x cubed 3 factorial plus x to the 5th 5 factorial plus x to the 7th 7 factorial. Right, so that's where that, sorry, alternating. Made that look weird. Ah. Right, so it's that alternating series that you're probably familiar with. And so in other words, sine of x is equal, what can be written as that, and that's where we get that small angle approximation. So sine of x is roughly equal to x, if you're only keeping the first order term. Others that are useful, cosine of x, might be obvious, is just the other terms. Right, so x to the fourth over 4 plus x to the 6 over 6 factorial plus minus and so on. Our friend ln of 1 plus x, we already saw the summation form of it, but if we write it out, it's x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. That's a 3 plus minus and so on. Right. And you can show that, for example, the sine, both the sine and the cosine functions converge uniformly for all values of x. For the natural log, this converges uniformly in the interval -1 to 1. Okay. Okay, where are we? All right. So that's Taylor expansion. And again, just to remind you, what we're doing is looking at a function and we're saying successive approximations of the change in the function around a particular point, right? Okay. Now, okay. Next we have the binomial expansion. And where does the binomial expansion come from? How do we get the binomial expansion? Well, the hint is that we already used the Taylor expansion, so that's probably important. What's the usual form? What are we usually looking at when we do a binomial expansion? What's the functional form that we usually use, that we're usually looking at? All right, so if I were to write f of x equals something, that would automatically, you would think I need to use the binomial expansion. What's that function look like? Did you say something, Nick? Can't hear you. Did I mute? No?
Is it working now?
Okay, yes.
Okay. 1 plus x to the n.
Right, 1 plus x to the m. And in fact, the binomial expansion comes from a Taylor expansion of this function, right? Basically, this equals 1 plus mx plus m times n minus 1 over 2 factorial x squared plus so on, right? So it's actually, technically, this is a Maclaurin expansion, right? Because this is expanding over small values of x, which we mean small values x being close to 0. Right? So that's where the binomial expansion comes from. The definition then is we take 1 plus x to the m, and we can write that as a series, this time from n equals 0 to infinity, of m factorial over n factorial times m minus n factorial times x to the n. And one way of writing that is the over notation. Has anybody, you've probably seen that? This is why my calculus teacher, the one who told me about factorial, sorry, basically hit us with chalk if we ever said dividing was something over something. Because technically, when we talk about over, we mean that for binomial statistics. All right, so that's just the compact way of writing that, where m over n is defined as m factorial over n factorial times the difference between the two. It's worth pointing out here, so sidebar, that we can have integer and negative values for the factorial. This comes from the actual definition, the integral definition of factorial. So the integral representation does anybody know what the, not necessarily what the form is, but what the function is that generates the factorial? Minus? You want to turn your,
Yeah, it's like a summation, but you use a capital pi instead of a sigma. I'm blanking on the name.
so that's the pi function, but you can represent it as an integral too.
Oh,
so,
sorry.
Pi, oh no, it's okay. So the pi function is related to something that you probably have seen somewhere. I don't know where, either quantum or thermal. The
Quantum
gamma
field theory
function
textbook.
depends on the, so you can represent, and this would be in the general case where z is a complex number. This factorial would be represented as the integral from 0 to infinity of e to the minus t times t to the z dt. That functionally gets you both the integral representations for factorials, but it also allows you to write the half integer, or the half integer representation. So, and we will see this, holy crap. We'll see this when we talk about special functions. 1/2 factorial, if you follow this integral, is square root pi over 2. And this comes from, again, the gamma function. Basically, gamma of n plus 1, which is the integral that I wrote up to the left, is equal to n factorial. If you use the pi function, it's basically pi of n. So it's just two different ways of writing it. And n plus 1/2 factorial is equal to pi halves times 3/2 times 3/2 times 5/2 up to n plus 1/2. Okay, so for positive values, you have that. For negative values, stop. Okay. Minus 1/2 factorial is equal to root pi. Minus 3/2 factorial is equal to minus 1/2 factorial over minus 1/2, or minus 2 root pi. That is, you take a step back. Minus 5/2 factorial is equal to minus 3/2 factorial over minus 3/2, or 4/3 root pi, if I did the math right on that. Anyway, that's just a nice little jaunty side note. We'll actually need to use that in the example that I'm going to do in a minute, but we are going to see these things later on in the course. Okay. Again, probably not going to need that right now, but it's useful to use. And again, it comes from this special integral Okay. Any questions? Okay, let's look at one example. I think we have time for one example. And this is an example that I'm sure that we've looked at before, but we'll expand on. Oh, sorry. There you go. Thank you. E equals mc squared times 1 minus v over c squared to the minus 1/2. All right, so if we let x be equal to minus vc squared, b squared, c squared, and m be equal to minus 1/2, then if we do the binomial expansion of this, we'll get mc squared times 1 minus 1/2 minus v squared over c squared plus minus 1/2 minus 3/2 over 2 factorial minus v over c to the 4th, and so on. So these are actually these terms, and this are using those fractional factorials. So what we get when we do this expansion then is our familiar E is equal to mc squared plus 1/2 mv squared plus 3/8 mv squared times v squared c squared. In other words, it's equal to whatever you want to call that, depending on whether you're comfortable calling it rest energy or not, plus an expansion for the kinetic energy, or the relativistic kinetic energy being 1/2 mv squared times 1 plus 3/4 v over c squared plus 5/8 v over c to the 4th, and so on. Okay. All right. And I think you've got 2 problems in the homework that look at that. And then there's another example that looks at like the Doppler, expanding the Doppler effect. So these are things that you have seen probably to maybe here, right? One of the examples one of the problems that I've assigned, actually, let me take a look. I did want to be explicit about. So in the homework, it's hang on a second. Here we go. It's number 1.3.11. So on the homework, 1.3.11 is deals with an expansion for Dirac's relativistic theory, and it has E equals mc squared times 1 plus gamma squared, which is a constant that includes things like z and e squared and all of that stuff, over s plus n minus absolute value k, all of that squared, all of this to the minus 1/2, with s equal to absolute value k squared minus gamma squared to the 1/2, and k is equal to plus or minus 1, plus or minus 2, and so on. Okay, so that's the problem in the homework, and what the question asked you to do is expand it up to through order of gamma to the 4th. So you're to expand, keeping only terms up to gamma to the 4th. Where this becomes tricky and is much more interesting than what this appears to be is that you're not to have this as a function of S. So in other words, you need to substitute in for what the value of S is for this. In other words, you're going to have gammas and Ks and Ns, but no S. So when you substitute in what S is into this, you're going to need to take about 3 different expansions. In other words, 3 different approximations. You need to approximate this, and then approximate that, and then approximate that. Okay, and then as you do the multiplication, keep dropping terms that have gamma that depend on higher order than gamma to the 4th. But your answer should only depend, E should be a function, your expression anyway, of gamma, N, and K. Okay, everybody see that? Or at least what I'm asking you to do for this. If you just expand it out as written and just keep S in there, it's a 1-step problem and not particularly interesting. Okay. Have you seen this equation before? Yeah. Oh, Ines, you look so pained. What?
That's just what my face is.
Oh, okay. Right. All right, well, that actually, again, wraps up where I wanted us to be. Before I go, are there any questions? Okay, how's everybody doing? Good? All right, well, look for an email from me about stuff to do with the department, and just feel free to stop by office hours and let me know if you've got anything that's happening that I should be aware of, so that we're all kind of muddling our way through this. So at least it's sunny here locally. So are you guys in Two Rivers? You are? Okay.
Yes.
Where is everybody? Do you mind me
Rick and
asking?
I are in Appleton.
Yeah.
Soldier's Grove.
Okay.
Wautoma.
Okay.
It's like an hour from here or from there.
Where are you, Adrian?
I'm in East Lansing, Michigan.
Okay. Oh, so we're all pretty much on the same time zone. Is anybody outside the time zone?
I'm in the Eastern time zone.
Oh, right. Okay. Yeah. All right. Well, you get to sleep in then. Okay. All right. Well, that's it. I'll see you guys later. You guys take care.
You too.
Okay. All right. I gotta stop all of
Thanks.
this.
Bye, Meg.
Bye.
All right.
Bye, Willow.